Hi guys, so from today onwards we are going to start one of the very good subject, that is electronics, devices and circuit, and this subject will be presented by me. I'm Dheeraj Mishra, okay, and this subject will be basically for GATE, IES, PSU and state examination, okay. So each year you'll find around 8 to 12 marks question in a GATE examination. Like if I talk about GATE 2020 conducted by IIT Delhi, you might have seen various questions from electronic devices and they were very good question, and I haven't seen any institute has covered those topic in fact, okay. So sometimes what happens, in each year you will find some good questions and those topics are not covered. In fact, they cover those topics but they don't internalize those topic properly, okay, because they follow some old, outdated notes and outdated books, okay. So in this subject we are going to cover these subjects according to latest pattern of GATE 2021, okay. So this subject is going to help you to score maximum marks, okay, like 8 to 12 marks, okay. So let us take a look at first the course outline. What are the chapter we are going to cover in this course, okay. The very first chapter we will talk about is semiconductor physics, okay, because without semiconductor physics you cannot understand any electronic devices, okay. And the second chapter will be the PN junction. This is one of the generic electronic device, okay, PN junction here. So we'll talk about PN junction. And the third chapter we are going to see is bipolar junction transistor, which is very important. Why it is called bipolar junction transistor we will come to know, okay. And the fourth topic, which is very important, in the fourth chapter we are going to start we are going to talk about MOS capacitor and MOSFET. Here MOS stands for metal oxide semiconductor, and here FET stands for field effect transistor, okay. And the fifth topic will be of discussion optoelectronics. Here we will talk about solar cell, okay, because each year you will find some questions from solar cell as well, okay. And the last but not the least, that is integrated circuit fabrication. So here we will talk about some real time experience, okay. I'm going to share some real time experiences because I have done my MTech in VLSI design. So this chapter is going to be covered nicely, okay. So the very first question comes in our mind when we come across the word semiconductor here. So in this slide we are going to cover introduction to semiconductor, okay. So what is semiconductor? When we come across semiconductor, the very first question comes in our mind is why semiconductor? Why semiconductor is so important as far as we discuss about electronic device, okay, any electronic device if you name it, like PN junction, BJT, MOSFET, and anything you talk about, okay. And where semiconductor devices are used and why only semiconductor is important, why not metal insulator? So let me tell you guys, if you are not familiar with semiconductor, okay, like if I'm not familiar with semiconductor, I cannot record my video, okay. If semiconductor devices do not exist, we cannot record this video, okay. So do not think about this is kind of software or kind of thing, okay. Semiconductor is just a material, it has some wonderful properties, okay. And this brings you to discussion about semiconductor devices. Without semiconductor, electronic devices are not possible, okay. So we are going to answer why only semiconductor is important, why not metal insulator. There are three kind of materials: one is metal, one is insulator, and one is semiconductor, okay. So anything you talk about, like if I talk about laptop, nowadays you might have seen palm top, or anything you talk about tablet, pen tablets and all, they are all made up of semiconductor devices, okay. So semiconductor is very important. All electronic devices are made up of semiconductor, okay. So why only semiconductor is important, why not metal insulators? So let us see in next slide the conductor and insulator and semiconductor, okay. Conductor here refers to the metal only. The conductor is a material, okay, which conducts electricity like a metal, okay. So it is one of the good material which conducts electricity, okay, nicely. And insulator are like wood and glass which cannot carry electricity so much, okay. Like if you see any wood and if you apply some voltage, so you cannot have any current over there, okay. But the word semiconductor means those material whose conductivity can be tuned or tailored or changed by some means as per the need controllably. You can see here, guys, if you want to change the property of any material, okay, according to your need, so the word semiconductor is one of the best candidate in front of you. Okay, you can have various properties out of this material, and if you try to change the conductivity of conductor, already as you know that conductor has great infinite amount of conductivity, so you need less to worry about changing the conductivity of conductor. Okay, and insulator, there is, no use of changing the conductivity, okay, because its resistivity is so high, so needless to change the conductivity of insulator. Okay, but the semiconductor, the word semiconductor, whose conductivity lie between these two materials, okay, and those its conductivity can also be tuned or tailored or changed by some means. Okay, so we will see what kind of advantage we are going to get out of it. How can we tune the conductivity of semiconductor? Okay, we will see there are various methods we have, so we'll be talking in next slides. Okay, so keep in mind that same without semiconductor electronic devices are not possible. Okay, and semiconductor, according to your book definition, you might have seen various books such as Milliman Halkias, or we can say Dunant Neiman. Okay, this kind of definition is given. Okay, means those material whose conductivity. And now if you are having doubt regarding conductivity, so let me tell you guys, if you know about the resistance means what we, the ratio of voltage and current, and from resistance you know the resistivity, and the reciprocal of resistivity is known as conductivity. Okay, so but the word semiconductor means here again, let me repeat the definition here, whose conductivity can be changed, okay, by some means. There are various methods we'll talk about, such as doping. We will dope to change the conductivity of semiconductor. Okay, so according to our need, in controllable fashion we can change the semiconductor. Okay, and changing the conductivity of conductor is of no use, because already the conductor is having good conductivity. Okay, so if I talk about the classification of semiconductors, what are the ways by which you can classify the semiconductor? Okay, the classification can be done in two ways basically. Let us talk about what are the ways. Okay, so semiconductor can be classified in two ways based on its purity. So based on its purity, if I talk about, so very first kind of semiconductor we can have is the pure kind of semiconductor. In this world nothing is pure. Okay, just we are talking ideal situation here. We will take two cases. Okay, always ideal and practical. Okay, so based on its purity means what? Any material, how can it be lot pure? Okay, so if I talk about in terms of purity, so pure kind of semiconductor can not exist, but we are just classifying it. Okay, so ideal situation we are considering like 99.9% your material is so pure, there is no defects, there is no vacancy. Okay, there is no external dopings, nothing is there. Okay, it is so pure. Okay, and the second kind of semiconductor we can say is intrinsic semiconductor. Okay, here intrinsic means what? Intrinsic means internal. Okay, so we can say that it is also a pure kind of semiconductor, guys, but there are some impurity we can say, because no material in this world is so pure. Okay, so if there is some impurity, so those impurity if we are able to compensate intrinsically, then we can say those kind of material is known as intrinsic semiconductor. Okay, and the third one is if we are going to introduce some intentional impurity into intrinsic semiconductor, then we can say that is extrinsic semiconductor. Okay, here ex word refers to what? External. Okay, if you are introducing some impurity externally, and that is intentional impurity. Okay, you are introducing into intrinsic, or we can say pure kind of semiconductor. Why we are introducing some impurity? It is having some, we are going to see some advantage as well, we will see. Okay, if you want to change the conductivity, we are going to do all these things. Okay, and the second way of classifying the semiconductor is on the on number of what elements. Okay, so from the periodic table, if you take like if you take from the fourth group one uh, one element, that is silicon or germanium. Silicon is widely used semiconductor as far as the electronic devices are concerned. Okay, why silicon is so important, we will talk about it. Okay, you might have seen also in the gate syllabus, each topic is having and ending with silicon, like energy bands in silicon, intrinsic and extrinsic in silicon. Try to look your gate syllabus. Okay, so if I pick up only one element from the fourth group of periodic table, so we are going to classify our semiconductor based on the number of elements, that is elemental semiconductor, or we can say simple semiconductor. And if you're going to see, we are going to take two elements from third and fourth group. Okay, here gallium arsenide, indium phosphide. So we are going to have the compound semiconductor. Okay, these are known as binary. Okay, or if we club three elements, okay, from the periodic table, we can also have the ternary kind of semiconductor. So these semiconductors are known as compound semiconductor. They have wide variety of application in optoelectronic devices. Okay, it has also huge band gap. Okay, huge band gap means what? Like if I talk about silicon, so it is having like around 1.42 electron volt band gap. We will talk about it, all these things. Okay, so just only you have to keep in mind what you have to keep in mind. The application of compound semiconductor is in optoelectronic devices. Okay, silicon and germanium, where they are most widely used semiconductor, and they are known as elemental semiconductor. Okay, so guys, let me tell you one of the very important concept. Okay, before understanding any electronic devices, you might have seen in any lecture, people do not emphasize here. Okay, so let me tell you one thing. The Nobel laureate Herbert Kromer says that if you cannot draw the band diagram for semiconductor devices, it means that you do not understand the devices. I have given many interviews like ISC Bangalore, IIT Madras. So I have been seeing that, the very first question they ask from the, from band diagram. Okay, so you might have seen also in various lecture of electronic devices and circuit, they never emphasize on band diagrams. Okay, they directly take some PN junction and they start explaining, electrons are going from N to P, and the hole is going from transport, making transition from, you can say, from P to N. Okay, but they do not discuss about band diagram. But Nobel laureate itself says that, he himself says that, Harvard Kromer says that if you cannot draw the band diagram for semiconductor devices, it means you have no understanding of devices, guys. Okay, so from I guess from gate 2016, IIC Bangalore started giving question from band diagram as well. Okay, so you can take a look. Okay, so therefore we will discuss in detail about following topics in basics. So the very first topic we will be seeing here is the band and band diagram, because these are very important concept before understanding any semiconductor devices. With the help of energy band diagrams, we will be able to understand qualitatively any semiconductor devices, and quantitatively as well. If you want to extract some quantitative information from energy band diagrams, so you can have, okay, regarding any semiconductor devices, you name it. Okay, and the second concept we will talk about is doping. Here you can see, guys, doping. And already I have told you what is doping. Doping means what? If you are introducing additional amount of impurity into pure kind of semiconductor, okay, to make extrinsic semiconductor. Okay, and then we will talk about electrons and hole concept here, because electrons and hole concepts are very important. Okay, here hole concepts, you need to understand where electron and hole exist. Okay, how can they exist, and what is the existence of hole and electrons intuitively, qualitatively, and quantitatively we will measure it also. Okay, and the next topic we will talk about is Fermi-Dirac statistics. Okay, without the help of Fermi-Dirac statistics, we cannot understand the existence of electrons and holes. Okay, so this is one kind of statistics we are going to see, and in this we will talk about the Fermi level and Fermi energy. This is also the topic where most of the faculty do not emphasize. Okay, and most of the students also do not worry about all these things. So we will in general we will talk about energy band diagrams and the Fermi level and Fermi energy. Okay, these are very very important topic. And the next topic we will talk about is under semiconductor physics is generation and recombination of electrons and holes. Okay, from this topic in gate 2020, in fact very good question was there. Nobody was able to answer this question. Okay, because in general people talk about how electrons are generated and how holes are generated and how electrons and holes are getting recombined. Okay, just they limit their discussion up to this only. Like people many faculty says that how electrons are generated, how holes and electrons are recombining. Okay, but they do not discuss more what are the generation and recombination concepts. Okay, so we like Sockley he we will talk about all those concepts also, right? So we will talk about different kind of recombination happens. Okay, and next topic we will talk about is transport mechanism. Okay, because once we will come to know that electron and hole exist, so how electrons and holes are transporting from like one place to another place. Okay, we will talk about this. Okay, so this topic will be like drift and diffusion. Okay, like if I talk about any device like p-n junction. Okay, so once we will join p type of semiconductor and type of semiconductor, okay, via some process, so how electrons and holes are transporting from one region to another region. Okay, so what are the mechanism like drift and diffusion, we will talk about it. Okay, how where drift is and where diffusion is. Okay, like without application of anything. Okay, anything we can have, there will be some diffusion, and if you are applying some voltage or electric field, you can have drift. And the last but not the least, we will talk about Hall effect. Okay, and you know okay, right. So the very first topic here under semiconductor devices are, like I told you, without understanding the band and band diagram, you cannot understand semiconductor devices. Okay, right. In fact, when I was preparing for gate examination, I had also no knowledge about energy band diagrams. We were just going through some books, and we were trying to take some equations from that book and try to mug up those, and while going through some questions, we used to take some information, plug those information into formula and get the answer. That's it. But now as far as the gate level is concerned, now question has been asked, you know like any topic they can ask anything. Okay, slightly some complication is there now, so you need to understand these things. Okay, okay, so most important concept of semiconductor devices or semiconductor is called energy bands, right? So when you come across the energy bands, okay, what kind of question comes in your mind? I may say that like you might have you may ask that how bands are formed. Okay, so you can see guys, this the y-axis is energy and the x-axis is distance. Okay, so these are the, just we can say, abstract model. Okay, we can say this band is a filled band where electrons are there. Okay, and this is empty band. Okay, we will also in future we will call this band as valence band, this band is conduction band, and the separation between these two is known as forbidden gap or energy gap. So we will talk about it, and based on the energy gap, the very important concept, that is energy gap, we will be able to classify the kind of material like semiconductor, conductor and insulator. Okay, in future, so you have to keep in mind these two axes. Okay, because in future we will also talk about the reciprocal of distance. Here we are talking about the centimeter. Okay, only distance. Okay, but in future we will also talk about energy band diagrams with respect to reciprocal of the distance. Okay, right. So now the question is, what are these bands and where have they come from, and why are these bands getting formed? These are the questions we are going to answer. So to understand this, one has to go into fundamental of each atoms. Okay. Now we will go into some each atoms, and we will try to understand how these bands are getting formed and where have they come from. Okay. So like from the fourth group only we will take one element, that is carbon. There is another element, that is silicon, germanium and all. Okay. But primarily we will take one simpler example, that is carbon. Okay. It is having 6 atoms. Okay. Single element we are taking just. Okay. So it is having 6 atoms, right? So if I talk about the electronic configuration, you can see 1s2, 2s2, 2p2. You might have studied these concepts in your chemistry or physics in your 11th and 12th. Okay. So you also might have seen these orbital models, okay, where electrons are there. You can see, guys, we are having 2 electrons in first orbit, and how many electrons? 4 electrons are in the last, here we can say in the valence orbit. Okay, we can say, right? So we are having 4 electrons, right? Okay. So though carbon is not considered as a semiconductor, we will come to know why it is not considered as semiconductor, but some form of carbon is also there which behaves like a semiconductor. Okay. But not all carbons atoms are, not all this kind of element behaves like a semiconductor, because it has huge band gap. Okay. We will talk about what is band gap. Okay. So you can see, guys, this is how we place electrons in the orbits. Okay. So in single carbon atoms, we can say in 1s we can say there are 2 electrons, you can see, guys, and there are 2 states. Okay. In 2s there are 2 states again, and there are 2 atoms, 2 atoms, you can see. Okay. 2 electrons. And in 2p you can see, guys, there are 6 states, but we are having only 2 electrons. Okay. But in crystal, each carbon atoms are arranged in fixed distance, which is known as lattice constant. Now, uh, like you're not from material science background, okay, you might not be good at material science, but let me tell you one basic difference between lattice and crystal. Okay. Without lattice you cannot have the crystal. Okay. There should be first the lattice. What is lattice? Okay, guys, lattice means what? If you are making arrangement of points in, like if you are putting uh, any points in linear fashion. Okay. So we can say there will be some lattice, and if you are putting some atoms on those points, okay, so that can form a crystal, right? So we are going to see, we will confine ourselves to understand the crystal, carbon crystal. So we will take 2D crystal. Here you can see, guys, 2D crystal. Okay. Right. 2D carbon crystal. So spacing between two nearby carbon atoms is known as lattice constant. That is fixed number of order of few angstrom. So you can see, guys, we are putting various. First thing first, there will be points. We are putting in this periodic fashion, right? And then we are putting some carbon with the help of some basis or motif, we can say. Motif is basically a bridge, okay, between that point and that atom, right? So this is forming a crystal, that is carbon crystal, carbon 2D carbon crystal. Okay, you can see between two carbon there is a distance that is known as lattice constant. Okay, right? So in crystal, the moment we try to bring two carbon atoms close, okay, like any crystal is there, so there will not be single carbon atom. Okay, there will be n number of carbon atoms. Okay, in any crystal there will be n number of carbon atoms. Okay, not only one carbon atoms, because if you will put one carbon atoms and one carbon atoms distance apart, there will not be any interaction. like like there are two friends, if they are sitting very far from each other, so how can they have interaction? Okay. So like in the class, like 90 guys are there, 90 students are there. Okay. So if they will be sitting nearby each other, so they will be interacting each other. Okay. In the same analogy, we can say that if we talk about any carbon crystal, so there will be n number of atoms. Okay. So in crystal, what happens, the moment we try to bring two carbon atoms, okay, two carbon atoms, or we can say n number of carbon atoms, then atoms of discrete energy levels. You can see guys, these are the discrete energy levels. You can see in 1s there are two states, this is one energy level. These are the discrete. You can see guys, this is the energy, and energies are discretized here, you can see. Okay, so the atoms of discrete energy levels interact each other, then each discrete energy levels which is sharp will start splitting into bands. You can see guys, I have shown here, this is the energy level, discrete energy level, which is sharp enough. Okay, so they will split into the bands. And what are the band? If somebody will ask what is the definition of band, so you can say these are the continuum of the states. Okay, because there will be n number of atoms. Okay, so there will be many discrete energy levels, they will interact each other, so they will be splitting into bands. So the simple definition of band is they are the continuum of states, right? So continuum of states or levels which appears as a band. This is very basic definition. Okay, so let us consider large number of atoms, which is n. Okay, in any carbon crystal there are large number of atoms, we can say n number of atoms. Okay, so now again we are taking this axis, y-axis, where energy is there, and this is the distance. Okay, so guys, here you can see we are not considering here, you can see we are not considering 1s2. Okay, we are starting with 2s2 where 2n number of electrons are there, because if there are 2n number of electrons, 2 state means if 2 electrons are there. Okay, so 2n electron will be there. Okay, consider large number of atoms, which is n, right? In 2s2 2n states will be there, and if there are 2n states, so 2n electron can be there. Okay, and in 2p2 6n states are there, but 2n electrons are available only, right? Okay, so this is the distance, right? This is the distance. In future we will also see that between two carbon atoms the distance will be referred as interatomic distance. Okay, interatomic spacing, we can say. So if we are bringing n number of carbon atoms very close to each other, so you can see guys, we are going in this direction, you know, from right to left. Okay, you can see the arrow here, we are decreasing the distance between two atoms. You have to imagine like this. Okay, because we cannot show n number of atoms here. So if you are bringing various n number of atoms, you know, very close to each other, as the distance becoming you know, smaller and smaller, okay, between the n number of among n number of states and n number of you can say electrons, so you can see guys, they are merging here, you can see, so they are recombining, and this, see, here will be what, here will be here 2n electrons means 6n states are there. Okay, here 2n electrons, right? So here will be what, here will be what we can say, total how many states will be there, 6n states plus 2n states, so here will be 8n states. So this will be the merged state. Okay, so in order to maintain continuity, you can see guys, the more interatomic spacing will be decreased. You can see guys, the distance between two atoms will be decreased, so they will be splitting into bands. You can see guys, here they will be maintaining continuum here, so they are splitting into bands. So here 8n states are there, but how many electrons can be occupied here? Only 4, because we are having 4 and 2n electron and 2n electron, total we are having 4 electrons. Okay, but here states are 8n states available, right? But here will be 4n electrons. But as you know that initially, if you are not giving any kind of energy to the electrons, so they will be having low energy. Okay, so we can say that entire 4n electrons which is available in merged state, they are 8n states here. Okay, so all 4n states, 4n electron will be here, 4n states, here 4n states. Okay, so all electron will be in this band. Okay, in the lower energy level, you can see, right? So if I define this distance, this is R equilibrium. Okay, where two bands will be splitted and there will be one gap this huge gap is known as energy band gap. Okay, this huge gap. So initially what we have done, we started with 2n electrons, 2n states, 6n states, 2n electrons. Total we are having 4n electrons, and total state we are having 8n states. So 4n electrons is there. Okay, and all 4 electrons are sitting in this band, and this band is completely empty. Okay, so in future we will also define this band is known as valence band, because 4 electrons are there and this band is empty. Okay, so this will be known as conduction band. Okay, and why it is known as conduction band, we will talk about it. Okay, once electron will move from here to here, so electron will become free, so they will be able to take part in conduction. That's why the band containing those electrons known as conduction band, right? So between these two, you can see guys, these bands are splitting, so there is a gap. But in this merged state, you can see guys, there is no gap. Okay, so the material will be falling under this merged state will be metal. Okay, because in metal there is no gap, but in semiconductor there will be a gap, right? Okay, so this is what the actual picture of bands formation. Okay, band formation, how band is splitted and how bands are formed, right? So you need to understand this kind of picture you will find in each book. If you talk about Halkias or Donald, any book you talk about, you will find this kind of pictures. You can understand from there. Okay, so we do not consider innermost orbital, that is 1s2. People will definitely ask why we are not considering 1s2. We are only considering 2s2 and 2p6, right? So 1s2, while forming a band, it does not contribute so much to energy band gap formation. Okay, 1s2 is one of the very lowest energy discrete energy level. It does not contribute that much. That's the reason we do not consider, okay, in our discussion. Only 2s2 and 2p2 contribute to have energy band gap formation. Okay, and here R equilibrium is the distance at which energy bands are formed. So this is the equilibrium distance where energy bands are formed. Okay, less than this R equilibrium there will not be any energy. You can see guys, see, if you talk about here, okay, here, so these are the merged states. So okay, so your bands are not splitted here, right? But at this we are defining this R equilibrium, where you can see guys, there is a gap and there are two bands. Okay, so these merged states are splitting. Okay, right? Why they are splitting you already know, because many discrete energy level they will interact each other and they will be splitting into bands, right? So the conclusion here is the metal does not have any band gap. You have to keep in mind always, metal does not have any band gap, and the metal will be here at n. Okay, 8 n states are there and 4 n electrons are there, right? There will not be any band gap. Okay, now if somebody will ask, can we define the band gap of insulator? Many people define. Okay, in many books you will also find those material whose band gap is so large. Okay, so we can say that that is insulator. Okay, quantitatively some kind of information is given in each books, but let me tell you the fact that in insulator like glass, the band gap concept will come into picture only when the material is sort of crystalline. Okay, if material is not crystalline, you cannot define the band gap, guys. You cannot define the band gap. Okay, so now the question will be, what is crystalline, right? If you're not a material scientist, if you do not have background of material science, you cannot understand crystalline. But let me explain here what is crystalline. Already you know the crystal, what is crystal, right? So crystalline material means what is crystalline means no matter in which position of a lattice we go, any direction you go, it will always look the same, which means the arrangement of atoms as lattice point are always the same. Okay, means there is no defects or distortion. Like suppose we are having one class, and that is electronic devices and circuit class, and there are 90 students, okay, sitting in the class. If they are sitting in proper manner, okay, in proper fashion, okay, so if we are going to see from the back, we are not going to differentiate, okay, right? Everybody will look like same. Okay, so crystalline is like that. If no matter in which position of a lattice we go, it will always look the same, which means the arrangement of atoms as lattice points are always the same, means there should not be any defects or distortion, right? So note, this is very very important notes. Okay, you will not find this kind of note in any coaching institute, in fact material. Okay, so technically speaking, only for crystalline material we can define the band gap, guys. If your material is crystalline, you can define the band gap. But even that, qualitatively one can assign band gap to insulator as well. Okay, so guys, qualitatively you can assign any number to this kind of insulator. Okay, whether it is crystalline or not, right? But you cannot define the band gap if your material is not crystalline. Qualitatively one can assign band gap to insulator as well, which is very very high, pretty high. Okay, like 6 electron volts. So we can say, if somebody will ask, if band gap is 6 electron volt, okay, so those kind of material is known as insulator, like wood and glass. Okay, and carbon is also having 5 electron volt band gap. Okay, so then only we can say carbon is not a semiconductor. Sometimes in years they ask this kind of question, right? So guys, we have got three kind of bands. The very first band is valence band, the band containing valence orbitals or valence orbital electrons. In the outermost orbit there will be electrons, like 4 electrons are there. If your element belongs to fourth group of periodic table, so 4 electron will be in the outermost cell, outermost orbit. If they are containing into any bands, so they are known as valence bands. Okay, right? And those electrons do not have any amount of energy. Okay, right? If we will give some energy to valence electron, okay, so they will be able to go from valence band to conduction band. So those so band containing free electrons, so those electrons will be free, because in the, or if you see orbital model, okay, so electrons which are very close to nucleus, they are tightly bound. Okay, there is some force. Okay, right, centripetal force we can say, right? So they are attached with the nucleus. So in order to break that force, okay, you need to give some energy to electrons. Or we can say, in if I talk about any band diagram, okay, any band diagram, like this kind of band diagram you might have seen this kind of band diagram in your book. Okay, this kind of band diagrams. So if electrons are sitting here, which are like field band, okay, electrons are sitting here. So if you are giving some energy to, and that energy is greater than this energy, that is in a more than energy gap. Okay, so your electron will go from here to here. Okay, your electron will go from here to here, right? So they will leave some vacancy here, and in future we will call them hole. Okay, hole. Okay, once electron will go from this band, like valence band to conduction band, and electrons are becoming free. Now they are not tightly bound with the nucleus, so they can take part into conduction, right? Then only we can say that band is known as conduction band. And forbidden gap or energy gap means what? It is separation between valence band and conduction band, right? So guys, this is one of the physical parameter in entire electronic devices. We will consider this parameter, okay? Because we do not have electricity, okay? We do not have anything at present. So we will consider this temperature. With respect to temperature, we will always discuss the behavior of electronic devices, okay? Behavior of any material, anything you talk about, okay? Right. So temperature dependence of energy gap in semiconductor, how temperature is depending, okay, how energy gap is depending on temperature in semiconductor. Okay, the energy gap, the energy band gap of semiconductor tends to decrease as temperature increases. Somebody will ask, if we are increasing temperature, what will happen with the energy band gap? So if I simply say that energy band gap decreases, okay, so you will not be convinced. Okay, many people say like that. Okay, many people say that they claim that once the temperature rises, the energy band gap of a semiconductor decreases. Okay, but what is the reason behind it? You need to know the reason. So again there will be some physics, right? You must understand these concepts. So due to increased thermal energy, and how can we quantitatively say that what is thermal energy? E equal to kT, okay, kT, right? So here the amplitude of atomic vibration increases, right? If you increase the thermal energy, like if you increase the temperature, the thermal energy will increase, okay? So in the crystal there will be n number of atoms, right? So they will start interacting, so atomic vibration will be there. I will also show you some video clip, okay, at the end of the courses, okay. If you want to understand, you can comment below in the comment section. If you want to understand, if you want to see some pictorial representation of how, you know, atomic vibration is happening in the crystal. So once you increase the temperature, guys, due to increased thermal energy equal to kT, the amplitude of atomic vibration increases. In turn, interatomic spacing increases, okay. So interatomic spacing will be increasing, therefore energy band gap decreases, right? Mathematically, how can we, so you have to keep in mind, if somebody will ask, if the temperature increases, what will happen with the energy band gap, okay? How energy band gap of semiconductor depends on temperature, right? Okay. So you know, mathematically, if I talk about the energy gap, Eg, here you can see the function of temperature. So Eg naught means what? At zero temperature, okay, at 0 Kelvin, we can say Eg naught minus beta T, okay, where Eg T is the energy gap at temperature, okay, at temperature T, which is Kelvin. So energy gap is a function of temperature here, and Eg naught is the energy gap of, okay, energy gap at 0 Kelvin, and beta is the material constant, simply. So you need not to understand what is beta and all those things. Only you need to sometimes in previous gate examination you will find questions from Eg naught, okay, energy gap, what is the energy gap of silicon at 0 Kelvin for silicon and germanium. So you can see, guys, here we are taking some generic example, and silicon is most widely used semiconductor, because silicon is you know, we can say it, we are having abundance of silicon on the earth, okay, and also silicon is having great property. In future we will talk about one kind of property, that is insulator, silicon dioxide, okay. Because of that silicon is mostly used, okay. So Eg naught means what? Eg naught equal to 1.21 electron volt. You have to keep in mind, at 0 electron volt is the unit of energy, you can see, guys, and beta is the material constant, okay. So 3.6 in 10 power minus 4, and Eg as a function of temperature, you can see, guys, Eg naught minus, here we have plug this beta here, okay, in this formula. At 300K, if somebody will ask what is the energy gap of silicon, energy band gap of silicon at 300K, so you have to answer directly 1.1 electron volt, okay. So guys, here you can see at 0 Kelvin, okay, your energy gap is 1.21 electron volt, okay, but at 300 Kelvin it is decreasing by slight amount, you can see 1.1 electron, 12 electron volt, okay, right. So that's why we are saying that as temperature increases, the energy band gap of semiconductor decreases. So I'm showing you mathematical induction. So via mathematics you can better understand anything, right? Okay. And germanium means what? You can see Eg is 0.78. Sometimes we, you know, in the examination, in various PSU examination, they ask what is the value of energy band gap at 0 Kelvin, okay, right. So you can see again, guys, for germanium 0.72 electron volt, okay. So you have to keep in mind, once you increase the temperature, the energy band gap of semiconductor tends to decrease. And what is the reason behind it? Due to increased thermal energy, the temperature of atomic vibration here increases, okay. Now, so based on our previous discussion, okay, we will take one question that is very important question, and this will test your understanding, right? If you have understood entire course, sorry, entire lecture, right, so you will be able to answer this question, okay. And I think from my experience of teaching, since many years, I have found that whatever I discuss in the class, if I give question after discussion, many students are able to solve any question instantaneously. Okay, so let us take this question. So consider the following statement regarding the energy band gap of material. Okay, so guys, energy band diagram is very important. We will try to learn how to draw the energy band diagram for different electronic devices such as p-n junction, bipolar junction, transistor, you name it, any electronic devices. But once you understand how to draw the energy band diagram for p-n junction, you will be able to draw any kind of for any kind of electronic devices. Okay, in the interview they generally do not ask about energy, p-n junction energy band gap. They change something. Okay, we will talk about all those things, right? So consider the following statement regarding the energy band gap of materials. The very first statement is every material has a different value of energy band gap except metal which have no band gap. Okay, the very first statement is correct. Already I have discussed the semiconductor is having, there will be some band gap, and if material is not crystalline, then we cannot define the band gap, but we can assign band gap. Okay, right? So and also you might have seen from that model, metal does not have any band gap. Okay, the energy band gap is decided by equilibrium interatomic distance, which is different in different materials. Okay, which is also true. Okay, which is also true, already discussed, right? So this interatomic distance, right? Okay, first and second is true, already we have discussed. In semiconductor, energy band gap increase, you can see guys, in the semiconductor energy band gap increase as you increase the temperature, right? So guys, already we discussed, if you increase the temperature, energy band gap of semiconductor decreases, not increases. So your third option is wrong from our previous discussion, already we have seen here this statement. Okay, right? And the fourth but last one is the energy band diagram of real semiconductor, okay, cannot be represented by flat conduction and balance bands. Okay, so you can see guys, this is the actual energy band gap, okay, of any material. Okay, so guys, here you can see I did not show you something which is flat here, nothing is flat. Okay, you can see these are the bands, this is known as balance band and this is known as conduction band. They are not flat, but in various book you will find that this kind of energy band diagram. Okay, these are the abstraction. Okay, we are just putting some information. Okay, we are just putting some picture. Okay, but these are not real picture of semiconductor, right? So flat conduction and balance band is not possible in case of real semiconductor. Okay, by flat conduction balance bands due to presence of energy states in the forbidden energy gap as well. So energy states you know already, right? Okay, so of the following which of the above statements are correct? Okay, so you know that third option is wrong, so in all options you can eliminate as well. So D is not wrong. D here you can see guys, D is not correct, and C is not correct because third is present. Okay, A is not correct because third is present, because this is straight away wrong statement. Okay, only the answer is B, right? So you may be wondering now, once you take up the lecture honestly, you would be able to answer any question, be it an IES question or GATE question. Okay, so we'll take various example of from electronic devices. First let us cover some content, right? Okay,